Hello guys, welcome back. It is I, Dr. Mandis, talking to you today about electrochem, and in particular I want to talk about spontaneity, Nernst equation. Spontaneity is the exact same gig it was in thermo when we were talking about Gibbs free energy. Gibbs free energy talked about whether the reaction would occur or not. It, Spontaneous. If the free energy was negative less than zero, then it was spontaneous. Greater than zero, not spontaneous. For spontaneity of electrochemical potential, the meaning is still the same. Will the reaction occur or not? I think because we're dealing with electrochemical potentials, easy way to sort of explain spontaneity is just to define potential. Potential is a likelihood, man. That is it. So let's just compare two guys. Back to equilibrium, we had Martians under equilibrium and we had Smurfies, right? All right. If I say, hey, the Martian has the potential of getting an A in this class, his potential is 4. Okay. The Smurf's potential of getting an A in this class is 7. Who's got the greater potential? The Smurf. Both are probably going to occur, not so bad, but you would bet your money on the Smurf. He's got a better potential. What if I said, hey, the Smurf wasn't 7? I'm sorry, it was negative 7. Would you think it was going to happen then? Would you think he was going to get an A? His potential is negative 7. The Martian's is a freaking 4. No, you think negative 7 not going to happen. All right. If I compare a negative to a negative, I mean, neither one's probably going to happen, but hey, that negative 4 beats out the negative 7. So who's got the greater potential? The Martian, but it's still crappy. Okay. That's what we mean by potential. Just a likelihood. All right. Just a likelihood. A positive potential, it's going to happen. Negative, not gonna. All right. E naught is the potential, or E is the potential. So it's either going to be greater than 0, less than 0. If you like it, things being unsimplified, the work done by an electrochemical system is calculated by the total charge multiplied by that potential. Okay. To get the total charge, the Q, it's the number of moles times Faraday's constant, which gets us to this groovy little equation: work equals negative N F E naught. Well, that sounds great and ducky, but the maximum work is also the Gibbs free energy. So this work is really delta G naught. Knowing that, we can say, hey, delta G naught equals negative NF E naught, or delta G negative NFE. That relates delta G free energy to electrochemical potential. If you notice, there's an opposite sign in there. There's a negative. Since it's a negative, that means what goes for delta G is going to be opposite when we do the potential. And hey, when we simplify crap, hey, it was opposite. Positive potentials were spontaneous, negative potentials weren't. So opposite works. For a reaction to be spontaneous, either way of slice it, free energy less than 0, potential greater than 0, standard or non-standard. Non-spontaneous, free energy greater than 0, potential less than 0. Cool? All you're going to do usually is you calculate a potential, calculate a free energy. They say, hey, is the reaction spontaneous? If we just ask, hey, is the reaction spontaneous? Then look at what you're given. If you're given thermodynamic data, odds are delta G. If you're given a bunch of potentials, odds are you're going to go with E. Okay? While we're on the subject of free energy, before we talked about the Nernst equation and said, hey, delta G, delta G naught, RT, natural log Q, we can sub in here negative NFE and negative NFE naught, do some rearrangement, and the Nernst equation can be rewritten for potentials. There's one slight little wrinkle to it. This is a plus, that's a minus because of all the negatives. It's really easy to get confused. I get confused all the time. All right, just pay attention to it as best you can. All right, R is the gas constant. It's going to be 8.314 because we're dealing with energy. T is the temp. It's always going to be in Kelvin. And it's what it was before. It's the number of moles of electrons. It's the electrons that cancel. So we'll see that in a couple different examples. F is Faraday's constant. There's an easier format of this, but for the most part, you don't really need it. And most of you guys are using little mini computers called calculators, so I don't sweat the other format. Okay. Thing that you're typically asked about is, if to evaluate this side of things. As Q changes, what does the effect of Q changing have on E? And basically if the product, since Q is products over reactants, as it gets bigger, that natural log term is going to get larger, and so you're subtracting a larger number from E naught, the potential actually goes down. If the reactants get bigger, then the natural log term's getting smaller. So you're subtracting a smaller number. In fact, the natural log term gets negative, and a negative of negative makes positive, it adds in. So you just need to work the ratio of Q. And we're going to do an example of that, so don't panic about it. Here's the first part of the example. Hey, given half reactions, can you give me the overall reaction and say whether it gives free energy and all that, calculate the potentials. So if I give you this info here, which I did not rewrite again, because golly gee, there's a lot on here. If I give you that, can you add them up? And hopefully you can add them up, okay? I didn't add up in here because I didn't want to do it, but this would be, if this is 2 electrons, then you'd have to multiply by 3 and multiply that by 2, okay? And that's 6 electrons, that's 6 electrons, okay? And then you can balance this stuff out, that's, the ours would be 2, things would be 3. The importance that you need to know it's 6 comes later with that n, the number of moles of electrons. If you look at the electrochemical potentials, negative 0.76, negative 0.036, a lot of students think negative 0.76 is bigger because it's bigger, like 0.76 beats 0.036, but they're negative numbers. So the 0.036 is actually bigger. Think of the number line. There's 0, positive numbers here, negative numbers there. The more you go to the right, the bigger you are. 0.036 is more to the right. It's an easy mix-up to do, especially if you're hustling through your problems. So anyway, this is your bigger potential. This is the smaller potential. So you flip the smaller one. So the negative is going to become a positive, and that's why it's a positive 0.72 volts. Plugging that 0.72 volts into delta G naught equals NF E naught, that'll help us solve the problem. And that's where the 6 moles of electrons come from. It's a really common question. Students don't know whether it's the 3 or the 2. It's neither. It's what you cross multiply and cancel out. So it's the 6 moles of electrons. And you just crank through the math. That's coulombs per moles electrons. Forgot to type that in there. Delta G is negative 940, negative 4,002, negative 420 kilojoules. Excuse me. So this, wow. What you have is a volt coulomb, okay? Because this is coulombs per mole electron. So you end up with a volt coulomb. And that can be confusing because most people don't know it. A volt is coulombs meter squared per second cubed amp. Amps, seconds cancel from the coulombs. And basically you end up with a joule. So I'm just trying to show you why it's a joule. If you're my student, you don't need to know that. Delta G's in joules, you're good to go. But the question is whether it's going to be in kilojoules or joules. This equation gets to delta G in joules. The actual answer to this thing was like 4,000, was that many joules. I switched it to kilojoules. So it's kind of neat to know that it's in joules. The follow-up question, what happens to the value of the reaction potential if the concentrations are changed? Iron 3 is 0.1 molar. It's supposed to be a positive. And the zinc 2 is 1 molar. So here you have your Nernst equation in terms of potentials. You can plug in for Q. You can see that this side, because it's a natural log of a number greater than 1, it's going to be the natural log of 10. It's going to be a positive value. So you're going to have the standard potential E naught minus a positive value. And so E will be less than E naught. So this question here, all right, you could calculate it all out and to say it, but they're just saying what happens to the value. I'm not asking you to calculate the value, just what happens to it. All right, so just evaluate, save time from having to sub in all that junk and evaluate it and just say that it's going to decrease. If you're really into it, you can apply all these things to an equilibrium constant, because delta G naught is negative RT natural log K. There's a relationship between the potential and the equilibrium constant. So you can say that, hey, if the potential is greater than 1, then this has to be a positive value that's greater than 1. And so it can tell you by looking at the potentials, you can sort of evaluate the size of K and say which side is favored. Alrighty, so you've learned a ton here. Hope you like it. I'm Dr. Manis. I'll definitely talk to you later. Take care.